Hello everyone, this is Abhay from ECE 4 department. In this video, I'm going to talk about scaling function which comes under multi-resolution expansion. So first of all, what are scaling functions? Scaling functions means generally used to create a series of approximation of image differing by a factor 2 and approximating to nearest neighbors. So scaling functions are nothing but we are just making a number of approximations of an image by n factor, and generally we keep the factor as 2, and after that we will approximate it to nearest neighbors. So for doing this we have some prerequisites for doing scaling to understand scaling function in a better way. So generally, any signal f of x can decompose into linear combination of expansion functions. That is, f of x equals summation k alpha k psi k of x, where k is an integer index and alpha k is an expansion coefficient. Psi k of x is expansion function. Basically, if the expansion coefficients has a unique set, then the psi k of x are called as basis functions. So, and the expansion of set of psi k of x is also known as a basis for the functions. Hence, function space is formed which is closed span of expansion set. That is, we can write it as V equal to closed span of psi k, a set of psi k of x. So this is nothing but span of set of expansion function is nothing but we are taking a number of linear, we are considering all linear combinations possible with expansion set psi k of x. So hence f of x, if f of x belongs to V, that means f of x is in closed span of the expansion set. Let's consider expansion set comprises of integer translations. Integer translations is nothing but shifting operation in integers, integral shifting operations, and binary scaling. We will talk about it soon. It is nothing but a scaling function, but by a factor 2. And the function psi of x should be square integrable. So what is square integrable? A function psi of x is said to be square integrable if and only if it satisfies Euler's condition. That is, summation of minus infinity to infinity modulus of psi of x whole square dx must be less than infinity. If the psi of x satisfies this condition, then it is known as a square integrable function. So let psi j comma k of x be the expansion function that we are looking for, and it is satisfying the above norms. Then the expansion function should be look like this. The psi of j comma k of x equals to 2 power j by 2 psi of 2 power j x minus k. Here k determines the position along x-axis and j determines the width of the expansion function. As you can see here, k is psi of 2 power jx minus k. Here k is nothing but refers to the integer translations, and 2 power j is nothing but a binary scaling. Now we can further generalize our previous equation spanned over k for any value of j. So since our previous equation is spanned over only k, now we are also adding a variable j. So it will be something like this: vj equals to closed span of psi j comma k of x. So psi j comma k of x equals to 2 power j by 2 psi of 2jx minus k. So this is our expansion function. From the above equation, following observations can be made. We see here that we got here a binary scaling factor. So as we know, if the scaling factor increases, then the width of the expansion function decreases. So the j and the width of the expansion function are in inverse proportion. So as we go on increasing j, the width of expansion function goes on decreases. So what will happen is the subspaces of Vj will be increased, since more space is available and more functions will get added, so the subspace will increase. So what's the advantage in here is we can use it allows the functions with smaller variations and the finer detail to be included in the subspace, therefore resolution also increases. So as the expansion functions become narrower and narrower, we can use them to represent smaller variations and a finer detail that to be included in the subspace. Hence, as Vj increases, resolution also increases. So Vj, how Vj will increase? If J value increases, expansion width will decreases, expansion function width decreases, it will increase the subspace Vj. As the subspace Vj will increase, the resolution also increases. So let's take a scaling function of unit height and unit weight. That is nothing but a hard wavelet. So this is our scaling function, say of x equal to 1. It is defined over the interval only 0 to 1 and elsewhere it is 0. So we will substitute the scaling function in this equation and we will try to obtain psi of 0 comma 0 of x, psi of 0 comma 1 of x, psi of 1 comma 0 of x, psi of 1 comma 1 of x. So here psi of 0 comma 0 of x and psi of 0 comma 1 of x belongs to v0. And psi of 1 comma 0 of x and psi of 1 comma 1 of x belongs to v1, and v1 here is has some higher resolution compared to v0. That is a point to be noted. And so on substituting, we get psi of 0 comma 0 of x equal to psi of x, and psi of 0 comma 1 of x equal to psi of x minus 1. And psi of 1 comma 0 of x equals to root 2 psi of 2x, and psi of 1 comma 1 of x equals to root 2 psi of 2x minus 1. So like here psi of x minus 1 is nothing but the expansion function is getting shifted by 1 unit to the right side of the y-axis, and here the expansion function is getting scaled by a factor 2, and its width will become by 2. And here the expansion function is getting scaled and also shifted at the same time. So here is the plot of psi of 0 comma 0 of x, 0 comma 1, 1 comma 0 and 1 comma 1. So here as you can see, the height is 1 and the width is 1. Since it is psi of x, it is simply a hard wavelet. Now if k equal to 1, it will get shifted to 1 unit by right side. So this is the plot. And here if in 1 comma 0, what will happen is the width will get scaled, so it should become by 2. So here you can see it became half compared to the first one. Compared to the plot A, plot C has become half, and its amplitude is little bit high compared to the A. And the same thing goes here. It got translated to right side. So that's what that will happen here for j equal to 1 and k equal to 1. So from these figures, we can make the following observation. Width of the signal for j equal to 1 is half of the width of the signal for j equal to 0. Hence, for a given interval of x, we can define scaling function for j equal to 1 twice as many as the scaling function for j equal to 0. So here it means that here you can see for j equal to 0 and j equal to 1, 0 and k equal to 1, both plot has same width of 1 unit. And for j equal to 1 and k equal to 0 and j equal to 1 and k equal to 1, both plot has the same width of 0.5 unit. And here we can mathematically write j equal to 0 plot in terms of j equal to 1, k equal to 0 and j equal to 1, k equal to 1. Since the width is half, the width of j equal to 1 is half of j equal to 0. So we can mathematically try to write, mathematically try to write a psi of 0 comma 0 in terms of 1 comma 0 and 1 comma 1. So this is what we'll get if we try to write mathematically psi of 0 comma 0 of x equal to 1 by root 2 of psi of 1 comma 0 of x plus 1 by root 2 of psi of 1 comma 1 of x. So here 1 by root 2 we have scaled our amplitude since it is a little bit higher compared to 0 comma 0. So we scale the amplitude and simply take the summation and we got psi of 0 comma 0 of x. And this is the graphical proof also. Here the blue portion is nothing but 1 by root 2 psi of 1 comma 1 of x, and the red portion is nothing but psi of 1 comma 0 of x 1 into 1 by root 2. So this is the blue portion and this is the red portion. That's what you are seeing here, and we have taken the simple sum, and and the sum is coinciding with the psi of 0 comma 0 of x. That is nothing but this equation is correct. So what we have done here is we have represented v0, a expansion function belonging to v0, in terms of an expansion function belonging to v1. So it's nothing but it means that psi of 0 comma 0 can be decomposed into sum of V1 expansions. In order to decide what scaling functions to be used, it should obey four fundamentals of multi-resolution analysis. So the first fundamental is the scaling function is orthogonal to its integer translates. That is, the scaling function, if psi of x is a scaling function, then psi of x multiplied by psi of x minus k must be equal to 0, where k is an integer translate. So we can prove this by taking an example of har function. So har function, whenever its value is 1, its integer translates are 0. Hence, product of it with its integer translate will always be 0. Therefore, har function satisfies the first requirement for the scaling function. So we know that har function is defined for 1 over the interval 0 to 1. So if we apply integer translate, then the interval over 0 to 1 will all become 0. And somewhere the integer translate it will be 1. So the product of the integer translate of har function and a har is always be 0. Hence har function is a scaling function. We can say it means we can't say like that, but it proves like it satisfies the first rule, first fundamental for the multi-resolution analysis. So here, if the width of the scaling function becomes greater than 1, then it will become harder to satisfy this condition, since functions will be having overlapping part, hence product won't be 0. So if the width is greater than 1, and if we try to do integer scaling, then there might be a chance for the when we do product, there could be a chance there would be an overlapping. So when there is overlapping, then product won't be 0. If product is not 0, then it's not orthogonal. The subspaces spanned by a scaling function at low scales are nested within those spanned at the higher scales. So we have already seen before, subspaces containing higher resolution function must also contain lower resolution function. That is, the lower resolution function should be able to be decomposed in terms of higher resolution functions. This we have already seen before and we have already proved, and this is the plot we already know. So since psi of x is satisfying this, so we can say that it is obeying second MRA requirement also. So here we can see the lower resolution V0 is a subset of V1, and and the resolution V1 is again subset of V2. So here we can see the higher scales must also comprise the lower scales. So this is the phenomena we are able to express psi of 0 comma 0 of x in terms of psi of 1 comma 0 and psi of 1 comma 1 of x. We shouldn't assume that the hard scaling meets this requirement because of the support width is 1. Support width is nothing but the height is 1. Consider the following example. So we'll take an example of a scaling function of a support width 1, but its interval is between 0.25 and 0.75. And now we will try to compute psi of 0, 0, 0, 1, 1, 0, 1, 1. So when we try to represent psi of 0 comma 0 in terms of j equal to 1 expansion functions, we weren't able to do it. We can here I took an example of psi of 1 comma 0 and 1 comma 1, and I try to represent psi of 0 comma 0 by doing an amplitude scaling, but still I'm not able to represent decompose psi of 0 comma 0 in terms of psi of 1 comma 1 and 1 comma 0. So we can simply say here that psi of this function is not a scaling function. So the other two rules are the only function that is common to all Vj is f of x equal to 0. So this is pretty easy one. At j equal to minus infinity, we get closest possible expansion function of no information, that is v of minus infinity equal to 0, and this should be this should be available in all types of resolution. Then only we can tell that psi of x is an scaling function. And the another rule is, and last and final one is, any function can be represented with the arbitrary precision. So yeah, all measurable square integrable functions can be represented by the scaling functions. However, for some particular f of x cannot be decomposed to some coarse resolutions. Like if we take an f of x belonging to v1, that is 0.5 psi 1 comma 0 of x plus psi 1 comma 1 of x minus 0.25 psi 1 comma 4 of x. This function we can't decompose psi of 0 comma 0 of x in terms of this f of x, since it is very coarse to represent psi of 0 comma 0 of x. So these are the four fundamentals of multi-resolution analysis. If the psi of x obeys to all four above conditions, then we can say Vj can be expressed as Vj plus 1. So that is psi of j comma k of x equals to summation of alpha n psi of j plus 1 comma n of x. So what we have done is we have simply replaced our f of x with psi of j plus 1 comma n of x. So substituting, we know psi of j plus 1 comma n of x can be written in this format, that is 2 power j plus 1 by 2 into psi of 2 power j plus 1 x minus n. So we have simply substitute here, and this alpha n we have represented with h phi of n. So here h phi of n is the coefficients in this recursive equation, and this is also known as a scaling function coefficient. And h phi of n is a vector of the scaling function coefficient known as the scaling vector. So here the psi of x, the psi of j comma k of x changes with the psi of x. So hence psi of x is called the scaling function. And since we know psi of x equal to psi of 0 comma 0 of x, we simply substitute 0 comma 0 of x, that is root 2x of 2x minus n. Then we'll get something like this. So this equation is also known as refinement equation. So that's it guys, and I used the following references I have used to prepare the slides and the video. So thank you everyone.